the in the test tube. So in our next session we shall have a look at that. Tech Talks Education. Thank you for watching. Carbonate, and this is mostly the first test that you are asked to do. The first test, always when you have been given a substance under test, and if it is a carbonate, they will say you hit a spatula end full of the solid carbonate strongly until no further change. So with a solid, when you hit it, we don't see bubbles in this case. Bubbles are produced where we have a liquid or a solution. So in this case, we shall be able to get a colorless gas which turns moist blue litmus paper red Daniel, and I'm a teacher of chemistry. I'll be handling you in chemistry of ordinary level or level. So we shall be discussing with you ordinary level chemistry. Now, before we can move on much, let us look at what chemistry is. So let's look at the definition of chemistry. So chemistry is a branch of science that deals with the study of matter and the changes they undergo under different conditions. So, chemistry is a branch of science that deals with the study of matter and the changes that they undergo under different conditions, meaning that chemistry is a science subject, in fact, a pure science subject. So, let us look at what this definition tells us. Chemistry deals with the study of matter. We have been looking at matter many a time. And what is matter? Simply, matter is anything that occupies space and has weight. Now let us have a deeper look at what matter is. Anything that occupies space and has got weight. Now, if matter is anything that occupies space, it means that matter has volume, because the space that is occupied by an object is what we call the volume of that object. Then 2, we say that matter has got weight. So weight is the gravitational pull on an object. So an object which experiences that gravitational pull has got mass, meaning that matter also has mass. So a subject which, an object which is called matter has got volume because it occupies space. It also has mass. That's why it has got weight. Now let us see what matter could therefore be. If you look around you, you'll find a marker like this. You find the wall is there, the seats or the chairs, and many other things. Think about the stones, think about air, think about water. These are some physical, simple examples of things that we encounter in our everyday life. That is what we call matter, because all of them have got volume. That means they occupy space, and they have got mass. So what I've just mentioned are what we call matter. So matter is anything that occupies space and has got weight. Now, we also say that in chemistry, we look at the changes that matter undergoes under different conditions. So let us try to see some of the changes that matter undergoes under different conditions. Let me give you some examples of changes. One of the changes is a simple one that we experience in our everyday life is ice changing into liquid water. Oh, ice, we always know it, that ice can change into liquid water. So ice is a solid, then liquid water is a liquid. Now the process by which a solid changes into a liquid has got a name, and that is what we call melting. It is a process of melting. So the process by which a solid changes into a liquid is what we call melting. It is called melting. Let me make it clearer here. It's called melting. Make it clear. This is one of the changes that matter can undergo. Now, that liquid water changing into steam. Liquid water is a liquid. It can change into steam, and steam is a gas. Now that process itself is what we call boiling. Mark you one thing, that boiling is very different from evaporation, because evaporation takes place only on the surface of a liquid, when the most energetic particles of a liquid tries to escape only from the surface. But boiling takes place throughout a liquid and at a constant temperature called the boiling point. So the process by which a liquid completely changes into gas is what we call boiling. This is one of the changes. So I've given you two changes here that matter can undergo. Ice changing into liquid water, then liquid water changing into steam. I want us to know that ice is water in the solid state. Then this liquid water is also water but in the liquid state. Then we have liquid water changing into steam. Liquid water is water itself. Even steam is water but in the gas state and at a high temperature. So these changes that I have mentioned already are changes which takes place without the substance itself changing into another substance, meaning that there is no new substance formed. And for that reason, these changes are what we call physical changes. So matter can undergo physical changes, and these are changes where or in which no new substance is formed. So I want to give you more examples of physical changes which matter can undergo. We have a change like melting, which we have already talked about. We have the process of boiling. We have got the process of condensation, where a gas changes back into a liquid. It's called condensation. Then we have got the process of freezing, whereby a liquid changes into solid. Then there is one unusual change whereby a solid changes directly into a gas, or a gas changes directly into a solid. And that's what we call the process of sublimation. So all these are what we call changes, and they are called physical changes. Now these physical changes takes place when something is applied. That's what we call a condition. In order for ice to change into liquid water, something must be there, and that thing is what we call heat. You are supposed to heat ice, and then it melts, it changes into liquid water, a process called melting. So the heat which is applied is what we call a condition for the reaction, for that change. In this case, if you look at the process of a liquid changing into steam in the process of boiling, you are even supposed to apply heat. That one is, the heat itself is what we call a condition for this change here. If you look at condensation, condensation involves a gas changing back into a liquid. So in this case, you are supposed to remove heat, or you lower temperature. That lowering of temperature or cooling or removal of heat is also a condition. So matter can change from one physical state to another when some conditions are applied. So this is one of the type of changes that matter undergoes, and that's what we call physical changes. We are going to also look at another type of change which is called chemical changes. So we also have chemical changes. So in a chemical change, a new substance is formed. So a chemical change does not involve these processes which we have just looked at, because a new substance is supposed to be formed. Like this piece of paper, if I burn it, it will change into ash. You will even see smoke forming. So the ash or the smoke which has been formed is not this paper here. So the ash is a new substance which has been formed, and that's what we call a chemical change. Matter can undergo also chemical changes apart from physical changes under certain conditions. Like for this paper, it has to be burnt. When it burns, it changes into ash. So the burning or the application of heat is actually what we call a condition for that change. So in a chemical change, a new substance is formed. So we have processes like burning of substances, not just heating, but burning. We have got the process of rusting which takes place on iron, rusting of iron. We have got the process of phosphorus reacting with air, what we call smoldering of phosphorus. It means that, by definition, relative atomic mass is the ratio of the mass of 1 mole of atoms of an element to 1/12 of the mass of carbon 12 atoms. And in simple, so for the sake of simplicity, relative atomic mass is given by the molar mass, or the mass of 1 mole of atoms of an element over, it's a quotient relationship, over 1/12 times O of the molar mass of carbon 12 atoms. So this is what we call relative atomic mass. Now, there are some values of relative atomic masses that are always given for our calculation. Remember what I told you, that in the mole concept, or with the mole concept, what we learn at a particular point, we apply it again in the next part for understanding the concept. So we shall always be given the relative atomic masses of elements. For example, I'm going to use the chemical symbols of the elements. Hydrogen has got a relative atomic mass of 1. Carbon has a relative atomic mass of 12. That is for carbon 12. Then we have nitrogen, which has got a relative atomic mass of 14. Oxygen has a relative atomic mass of 16. We have got sodium with a relative atomic mass of 23. We have got magnesium with a relative atomic mass of 24. We have got aluminium with a relative atomic mass of 27. Phosphorus has a relative atomic mass of 31. Chlorine has a relative atomic mass of 35.5. We have got potassium. Let me use sulfur first, with a relative atomic mass of 32. Potassium with a relative atomic mass of 39. We have got calcium with a relative atomic mass of 40. If you look at this, these are members, they are among the first 20 elements. Let me also add other elements, like I have copper with a relative atomic mass of 64 approximately. We have got iron with a relative atomic mass of 56. Let me also use zinc with 65. Let me use lead with the 207. Let me use iodine with 127. Silver with the 108. So these are the relative atomic masses of elements. So when you are given this, you just know you are going to use them. In this case, you will be using in our next, or we shall be using this one here in our next discussion of what we call relative formula masses. Please don't forget this, that you will be given this one here, but it is good for a candidate to also know them so that you apply them anytime. So thank you so much for listening. Okay, hello students. My name is Achelam Daniel, and I'm a teacher of chemistry. I'll be handling you in chemistry of ordinary level or level. So we shall be discussing with you ordinary level chemistry. Now, before we can move on much, let us look at what chemistry is. So let's look at the definition of chemistry. So chemistry is a branch of science that deals with the study of matter and the changes they undergo under different conditions. So, chemistry is a branch of science that deals with the study of matter and the changes that they undergo under different conditions, meaning that chemistry is a science subject, in fact, a pure science subject. So, let us look at what this definition tells us. Chemistry deals with the study of matter. We have been looking at matter many a time. And what is matter? Simply, matter is anything that occupies space and has weight. Now let us have a deeper look at what matter is. Anything that occupies space and has got weight. Now, if matter is anything that occupies space, it means that matter has volume, because the space that is occupied by an object is what we call the volume of that object. Then two, we say that matter has got weight. So weight is the gravitational pull on an object. So an object which experiences that gravitational pull has got mass, meaning that matter also has mass. So a subject which, an object which is called matter has got volume because it occupies space. It also has mass. That's why it has got weight. Now let us see what matter could therefore be. If you look around you, you'll find a marker like this. You find the wall is there, the seats or the chairs, and many other things. Think about the stones, think about air, think about water. These are some physical, simple examples of things that we encounter in our everyday life. That is what we call matter, because all of them have got volume. That means they occupy space and they have got mass. So what I've just mentioned are what we call matter. So matter is anything that occupies space and has got weight. Now, we also say that in chemistry, we look at the changes that matter undergoes under different conditions. So let us try to see some of the changes that matter undergoes under different conditions. Let me give you some examples of changes. One of the changes is a simple one that we experience in our everyday life is ice changing into liquid water. Oh, ice, we always know it, that ice can change into liquid water. So ice is a solid, then liquid water is a liquid. Now the process by which a solid changes into a liquid has got a name, and that is what we call melting. It is a process of melting. So the process by which a solid changes into a liquid is what we call melting. It is called melting. Let me make it clearer here. It's called melting. Make it clear. This is one of the changes that matter can undergo. Now, that liquid water changing into steam. Liquid water is a liquid. It can change into steam, and steam is a gas. Now that process itself is what we call boiling. Mark you one thing, that boiling is very different from evaporation, because evaporation takes place only on the surface of a liquid, when the most energetic particles of a liquid tries to escape only from the surface. But boiling takes place throughout a liquid and at a constant temperature called the boiling point. So the process by which a liquid completely changes into gas is what we call boiling. This is one of the changes. So I've given you two changes here that matter can undergo. Ice changing into liquid water, then liquid water changing into steam. I want us to know that ice is water in the solid state. Then this liquid water is also water but in the liquid state. Then we have liquid water changing into steam. Liquid water is water itself. Even steam is water but in the gas state and at a high temperature. So these changes that I have mentioned already are changes which takes place without the substance itself changing into another substance, meaning that there is no new substance formed. And for that reason, these changes are what we call physical changes. So matter can undergo physical changes, and these are changes where or in which no new substance is formed. So I want to give you more examples of physical changes which matter can undergo. We have a change like melting, which we have already talked about. We have the process of boiling. We have got the process of condensation, where a gas changes back into a liquid. It is called condensation. Then we have got the process of freezing, whereby a liquid changes into solid. Then there is one unusual change whereby a solid changes directly into a gas, or a gas changes directly into a solid. And that's what we call the process of sublimation. So all these are what we call changes, and they are called physical changes. Now these physical changes takes place when something is applied. That's what we call a condition. In order for ice to change into liquid water, something must be there, and that thing is what we call heat. You are supposed to heat ice, and then it melts, it changes into liquid water, a process called melting. So the heat which is applied is what we call a condition for the reaction, for that change. In this case, if you look at the process of a liquid changing into steam in the process of boiling, you are even supposed to apply heat. That one is, the heat itself is what we call a condition for this change here. If you look at condensation, condensation involves a gas changing back into a liquid. So in this case, you are supposed to remove heat, or you lower temperature. That lowering of temperature or cooling or removal of heat is also a condition. So matter can change from one physical state to another when some conditions are applied. So this is one of the type of changes that matter undergoes, and that's what we call physical changes. We are going to also look at another type of change which is called chemical changes. So we also have chemical changes. So in a chemical change, a new substance is formed. So a chemical change does not involve these processes which we have just looked at, because a new substance is supposed to be formed. Like this piece of paper, if I burn it, it will change into ash. You will even see smoke forming. So the ash or the smoke which has been formed is not this paper here. So the ash is a new substance which has been formed, and that's what we call a chemical change. Matter can undergo also chemical changes apart from physical changes under certain conditions. Like for this paper, it has to be burnt. When it burns, it changes into ash. So the burning or the application of heat is actually what we call a condition for that change. So in a chemical change, a new substance is formed. So we have processes like burning, of substances, not just heating, but burning. We have got the process of rusting, which takes place on iron. Rusting of iron. We have got the process of phosphorus reacting with air, what we call smoldering. Smoldering of phosphorus. So these are examples of what we call chemical changes. So in these chemical changes, new substances are formed. So here, new substances are formed. So let us now look at the calculation of empirical and molecular formula. Calculation of empirical, or what we call simplest formula, and molecular formulae of compounds. So we are going to look at this, and we should know that these are two different things, the empirical formula and then the molecular formula. Can we look at some simple example? Let's look at this example here. A hydrocarbon T consists of 85.71% carbon. Full stop. A. Calculate the empirical formula of the hydrocarbon T. B. If the molecular mass of the hydrocarbon is 28, determine its molecular formula. Given generally that carbon has got a relative atomic mass of 12, hydrogen with a relative atomic mass of 1. So let us try to see how we can go about with the calculation of the empirical formula of this hydrocarbon and then the molecular formula, given the relative atomic masses. And we can see from here that the percentage purity, the percentage composition of carbon has been given this 85.71% in this hydrocarbon T. Now, a hydrocarbon, we must know what it is. It is a compound that consists of carbon and hydrogen atoms only. That's a hydrocarbon. Meaning that if 85.71% is the percentage composition by mass of carbon in this compound, that means the rest is the percentage composition by mass of hydrogen. So in our solution that we are going to have right now, the first thing we need to do is to get the percentage composition, that is the percentage of hydrogen in this compound. If this one here, 85.71% is for carbon, it means that the rest that makes up to 100% is for hydrogen. So we shall have to subtract the 85.71 from 100. So 100 minus 85.71, and this one gives us 100 minus 85.71% gives us 14.29%. Please, you need to start by working out this, because you cannot go ahead and calculate anything when you don't have the percentage composition by mass of the second element or of the other element in that compound. So we have the percentage of hydrogen. Now let us go to the calculation of the empirical formula. When we are calculating the empirical formula of a compound, there are some steps that we are supposed to follow, and we are not supposed to skip any step. The first step is to write down the chemical symbols of the elements side by side in one row. So we start with the elements. These elements are carbon and hydrogen. Make sure that the chemical symbols are a bit far from each other, because you may have a long decimal number, so it should not contradict with what is under the next element. So in this case, carbon is here, hydrogen is here in one row. Then next is, we need to put down the percentage composition by mass of each element. So for carbon it is 85.71, and that of hydrogen is 14.29. That's the percentage composition. There is no need for me to put percent here, because I've already talked about it here. Next is, we need to know the values of the relative atomic mass of each element, which have already been given here. So for carbon it is 12, and that of oxygen is, that of hydrogen is 1. Next is, we are going to calculate the number of moles of each element in the compound using the percentage composition and the value of the relative atomic mass. So we now go to the step of getting the number of moles. So if we want to get the number of moles of carbon, we are going to divide the percentage composition, which is 85.71, by the relative atomic mass, which is 12. Likewise here for hydrogen, it will be 14.29. We divide it by 1. And then we put an equal sign to show that we are getting some values from this expression here. So 85.71, we have to divide by 12, and this one gives us 7.1425, and this one gives us 14.29. Now mark you this. Never try to round off. Let me put it here for you so that we don't forget. Do not round off. Reason being, if you round off in this case, then you'll be moving away from the correct answer. You'll be going to an approximate answer in this case. Make sure that you do not round off at this stage. Even if it is a very long decimal number, you leave it the way it is. Then we are going now to what we call the mole ratio. Remember that we are moving towards what we call the empirical formula, which is a formula which expresses the ratio of the number of moles. That's what we call the mole ratio. So in getting the mole ratio, we shall be dividing the number of moles that we have got from here by the smaller number of moles. So this one, the mole ratio will be 7.1425. We are going to divide it by itself because it is smaller, 7.1425. Even this one here, 14.29, we divide by 7.1425. what we get from here is the correct answer, which will be our mole ratio. Please still do not round off anyhow. So this one gives us a ratio of 1 to, let's get this, 14.29. We divide by 7.1425. This one gives us 2.000700035. Now at this point, when you have got the mole ratio, you need a whole number, or you need whole numbers here, but this one is a decimal number. When you reach this point, you are free to round off to 1 decimal place. Try to round off to 1 decimal place and see what you get. You are supposed to get either a whole number or a number which is simple to deal with, even if it is a decimal number. So this one gives us a ratio of 1 to 2.0, and 2.0 is just 2. Now, let me use this part here. When you have got this, please show that the number of moles of carbon atoms here is 1 in this ratio. So it will be C1H2. This one tells me that the ratio is 1 to 2. If you leave it, or suppose it was say 2 to 2, if it was 2 to 2, then in this case it means that the ratio is even 1 to 1. So we first give this one to show us the actual ratio, then we can conclude that therefore the empirical formula of T is CH2. Even if we don't put this one here, it's already here. But we have put this one here for the purpose of showing that the mole ratio is 1 to 2. So this is the account of how to get what we call the empirical formula. Follow these steps here. So that is that. We are remaining with getting the molecular mass. So let us wind up very fast in getting the molecular formula, in this case very fast. The molecular formula of this compound here, as we have already seen, we are supposed to multiply the empirical formula by the simplest factor n, which we don't know. So our molecular formula is CH2. If we multiply it by some value n which we don't know, it must give us the molecular formula whose molecular mass has already been given to be 28. So this one must give us 28. Now what we are going to do is, in order for us to get the value of n, we are going to get the empirical mass here in this case and then make n the subject. So our empirical mass will be n times 12 plus 1 times 2. It should give us a total of 28. So 12 plus 1 times 2 is 12 plus 2, which is 14. So this one times n gives us 14n, giving us a total of 28. Now this is a very important step that will give us the value of n. N is got by dividing 28 by 14. Don't forget this step here. It's a very important step, because if you get this, if you divide this one here by this, you are going to get the value of n, and n in this case becomes 2. Then finally we substitute for the value of n. We just substitute directly and say the molecular formula of T is, then let's substitute for the value of n. In this formula here, we shall multiply the number of carbon atoms by 2, which becomes C2H, and then this is 2 times 2, which gives us a total of 4. And that is the formula of the compound. That's the molecular formula. So what we have seen is how to get the empirical formula of the compound and then the molecular formula of the compound, given the molecular mass of the hydrocarbon or of that compound. Remember, if it was the vapor density, then we would multiply the vapor density. If this one was the vapor density, we would multiply it by 2 to get the value of the molecular mass of the compound. So, thank you for watching in this case. So, when it loses its water crystallization, out of the 10, we remain with only 1 mole of water crystallization. So, we shall have Na2CO3 dot water. 1 mole of water only remains out of the 10. Never you be mistaken that since I'm seeing water, it should be a liquid. No, this is a formula of the compound, the solid compound. What remains after the loss of the 9 moles of water crystallization? So these ones get lost to the atmosphere. We remain with this. Now, remember that water crystallization is what binds the particles of this compound together to form a crystal. If we lose the water crystallization, that means that we are losing also the crystalline nature or the crystalline nature of this compound here. So it gradually turns into a powder. So what we shall observe is that these transparent crystals will have to tarnish. That means that the transparent nature will have to change. It starts becoming dull and finally turns to white. Actually, it will also be turning from a crystal to a powder gradually as it loses the water crystallization. Then our observation is that the transparent crystals tarnishes in appearance and gradually turns into powder. Then in part 3 they are saying we should give the name given to this process by which a compound loses water crystallization to the atmosphere when left exposed in air. So that process is what we call the process of efflorescence. Take note of the spelling here. It is the process of efflorescence. And then finally, we should name some other substances that behaves in the same way like this compound here when left exposed in air, meaning that other substances that can undergo efflorescence. It also means that we are going to use hydrated compounds only because they are supposed to lose their water crystallization to the atmosphere. So we are supposed to name, not to give the formula. So we are going to give the name. One of them is we have sodium sulfate 10 water. It undergoes efflorescence. We have copper 2 sulfate 5 water or pentahydrate. That is also crystals that loses their water crystallization to the atmosphere when left exposed. I have iron 2 sulfate, iron 2 sulfate 7 water. It also loses its water crystallization to the atmosphere. So that is that with the calculation involving a hydrated compound. So thank you so much for watching. Welcome back to TEP Talks. We are going to have a session of a continuation of calculation of empirical and molecular formula. Earlier on we had seen how to go about with the calculation of empirical and molecular formula. But as we proceed, let us try to see numbers that may try to give us some little bit of headache. So we are going to continue with the continuation of the calculation of empirical and molecular formulae of compounds. So let us try to look at another number here. Let us again use a hydrocarbon. A hydrocarbon W consists of 82.76% carbon and the rest being hydrogen. The first part of it says calculate the simplest formula of W. Then the next part says if the vapor density of the hydrocarbon is 29, determine its molecular formula. Given that carbon is equal to 12 and hydrogen is equal to 1, let us look at how we can determine the empirical and the molecular formula of this hydrocarbon with the percentage composition by mass of carbon being 82.76, and then they say that the rest is hydrogen. Even if we have not been told that the rest is for hydrogen, we just know that a hydrocarbon consists of carbon and hydrogen atoms only. So since they have said that the rest is hydrogen, let us first start by getting the percentage composition of hydrogen. The percentage composition of hydrogen will be 100 minus 82.76, and this one will give us, let us use our calculator, 100 minus 82.76 this one gives us 17.24%. This is the percentage of hydrogen in this hydrocarbon W. Now let us go ahead and calculate the empirical formula using the steps that we have seen before. So we start with the component elements. In this hydrocarbon we have carbon and we have hydrogen. The symbols of the elements are written in the same row, side by side, but I said there must be some fair distance between the two chemical symbols, so that in case you get a long decimal number, it should not come up to down here. It should not conflict with the space for the values that should be under hydrogen in this case. The next thing is we need to write the percentage composition of each. So for carbon it is 82.76, for hydrogen is 17.24. Then let us also remind ourselves by putting down the relative atomic mass of each element. For carbon it is 12 and that of hydrogen is 1. Next easy, we are going to get the number of moles and as we have done before by dividing the percentage composition of each element by its relative atomic mass. So in this case for carbon is
82.76, we divide by 12. Hydrogen is 17.24, we divide by 1. What we get is the number of moles of each element in this compound. So let us look at that of hydrogen. That of carbon is 82.76. We divide by 12. Oh, it has given us 6.8966666667, and this one gives us 17.24. Please, I say that we need not in any way round off. Leave the values as you have seen from the monitor or from the screen of your calculator. Next is we are now going to the mole ratio. The mole ratio. So the mole ratio is got by dividing the two number of moles by the smaller number of moles. If there were 3, we would divide all through by the smallest number of moles. So here we are going to divide by the smaller number of moles. So it is 6.89666667. We divide it by itself by 6.89666667. Even here, the 17.24, we divide it by the smaller number of moles, that is 6.89666667. What we get from here will be our mole ratio. So our mole ratio will be a ratio of 1 to, let us get the other one also. So it is 17.24, we divide by that. And here we have got 2.499758337. Now we have an issue here. We have reached a point whereby our mole ratio is having a whole number and then a decimal number. At this point, you can now round off to one decimal place. That is if and only if we have got the mole ratio. At this point, when you have just got the number of moles, please do not in any way round off the number of moles. Leave them the way they are. But when it comes to the mole ratio, please, when you have got a ratio of 1 to some decimal number, first round off to one decimal place, and in this case it becomes an approximate value. It is approximately 1 to 2.5. Now, the point is here. In most cases, we look for a number which we can multiply each number of moles with in order to get a whole number. But the simplest way is here. What we are going to do is we shall have to convert this decimal number into a fraction. As you can see, we are having 2.5 as being our fraction. So we shall get the fraction which corresponds to 2.5 this way. Firstly, start with the lowest term of this decimal value here. The lowest term of the decimal value 0.5 is 0.5. Then from 0.5 we go stepwise, we go to 1.5. Then later on we shall reach 2.5. We shall get 2.5, a fraction which corresponds to 2.5, but progressively. So what gives us 0.5 in this case is a half. For me to get 1.5, which is the next value after 0.5, I'm going to add the denominator to the numerator and then maintain the denominator. So it will be 2 plus 1, giving us a total of 3/2. We maintain the denominator. Please try to enter this in your calculator. You're going to get exactly 1.5. Here, this one here, it is 2 plus 3, which is 5/2. So this is how we can get a fraction which corresponds to 2.5. Now we shall carry that fraction and bring it back here. So we have approximately a ratio of 1 to 5/2. Now what you do next is multiply both sides by the denominator. So we shall multiply this one here by 2 and this one also by 2. What we get from here gives us now the real mole ratio which we are going to use, or from which we are going to get the empirical formula. So this one becomes a ratio of 2 to 5, meaning that the empirical formula is C2H5, and we can therefore conclude that the empirical formula is C2H5. I want to take it through something small again. In case it is a 0.3, let us say, supposing we had a ratio of 1 to, say, let me use 1.299375154. If this was our ratio, still we are going to convert this one here into a fraction, but by firstly, if this one is our mole ratio, we shall firstly round off to 1 decimal place. This one becomes 1.3. Now, if it is a 0.3, make sure that you get a fraction which corresponds to the 0.3, but make it be a recurring decimal. It will give you a very good fraction which you can use the way we have used this one here. So let us try to see from here. Let's try to work it out from here. So if we want 0.3, if we want 1.3, we start from 0.3, but will be recurring, then we go to 1.3. So 0.3, a fraction which gives us 0.3 recurring is a third, 1 over 3. Then this one here becomes 3 plus 1, which is 4 over 3. Then we bring it back here. It will be approximately 1 to 4 over 3. Then multiply both sides by the denominator. So by 3. And it will be approximately a ratio of 3 to 4. And then your empirical formula will be this element here, 3. Then this element here, 4. That is how we can get a decimal number. Please, if you don't round off from here, then you are going to get a very good value down here, which when rounded off to the near, say to 1 decimal place, you can easily get a value which will be either a 0.5 or a 0.3, or it can be a whole number straight. So don't make a mistake of rounding off your number, or your number of moles in this case. Don't round it off, leave it the way it is. Use it until when you reach the mole ratio. When you have got it, then you can round off to 1 decimal place, and then you get a fraction which corresponds to that very value. Multiply both sides by the denominator and get the, in this case, you get the correct mole ratio. So that is how we can get it. And that was part A. We have got the simplest formula of the compound, and then the simplest formula is C2H8. Next is, they are saying we should calculate the molecular formula if the vapor density of the hydrocarbon is 29. So let me use this downer part here for calculating, in this case, the molecular formula of this hydrocarbon W. I believe that we have picked something here and here. How to convert the decimal value to a fraction, which we then use for getting our mole ratio. So let us try to see. In part B, we have been told that if the vapor density of the hydrocarbon is 29, what is its molecular formula? So we say that in getting the molecular formula, the empirical formula which we have got in this case, it is C2H5, we have to multiply by a simple factor n, and it will give us the molecular formula whose molecular mass is supposed to be given. But in this case, we have not been given the molecular mass, but the vapor density. So vapor density is supposed to be multiplied by 2 in order to give us the molecular mass. So let us use this one here. The vapor density we have multiplied by 2, and it is giving us the molecular mass. So let us try to work out the empirical mass. It will be n times the whole of 12 times 2. I've got the mass of carbon in this empirical formula. I'm adding it to hydrogen is 1, so it will be 1 times the number of atoms, which is 5. And the whole of this one should give us a total of 58. So let us work out the value of n. So 12 times 2 is 24 plus 5 is 29. So it will be 29n is equal to 58. And what is n? How do we get n? It will be 58 divided by 29, and our n is equal to 2. Please don't forget this step here. You know that if you are to get n, you are supposed to divide 58 by 29. Don't just say 29 n is equal to 58 and therefore n is equal to 2. It will not be correct. Show your working clearly. And as we have done it here, we have shown our working clearly. Now let us try to substitute for the value of n in order to get for us the molecular formula. So directly the molecular formula of the hydrocarbon W is, let's substitute for n here. So n is in this case 2. So 2 times 2 gives us 4. So it will be C4. Then we come to this. 2 times 5 is 10. So it will be C4H10. Okay, welcome back to Tech Talks Education. We are continuing with having a look at the calculation of empirical and molecular formula of compounds. We are going to look at something which is a bit new but closely related to what we have been doing. So let us try to see. In this case, you may not be given what we call percentage composition, but you may be given masses of the elements. So you should know how to deal with the masses of the elements when given and when it is not the percentage composition given. So let us look at these numbers well. When dry carbon monoxide was passed over 12 grams of a heated oxide of iron, comma, 8.4 grams of oxygen, 8.4 grams of iron remained. So in the first part, we are supposed to calculate the simplest formula of the compound. In part B, Roman 1, write equation for the reaction that took place, and then Roman 2, state the industrial application of the above reaction. So here we are given that the relative atomic mass of iron is 56 and that of oxygen is 16. So we are good to go. Now we are going to seriously think. We have been given that dry carbon monoxide gas was passed over 12 grams of a heated oxide of iron. This is the combined mass of the oxygen in this compound and then iron, which has combined with the oxygen. The total mass is 12 grams. Now, when dry carbon dioxide gas was passed over the heated oxide of iron, they said that 8.4 grams of iron remained. What happened in this case? We must understand the role played by carbon monoxide in this reaction here. Carbon monoxide is a reducing agent. So in this case, as a reducing agent, it removes the oxygen atoms found in the oxide of iron in this reaction here. So after removing all the oxygen atoms, then we remain with the only iron. So this 8.4 grams is the mass of iron only. So why is it that there is a variation in mass here? There has been a reduction in mass from 12 grams to 8.4 grams. That one is simply because carbon monoxide removed those oxygen atoms and the mass had to reduce from 12 grams to 8.4 grams. So they say that is the mass of iron that remained. So we don't know the mass of oxygen. We have only the mass of iron. So let us work out the mass of oxygen. So the mass of oxygen is equal to the 12 grams minus the 8.4 grams that remained. And what we have in this case is 12 minus 8.4, which is 3.6 grams. This is the mass of oxygen only in this heated oxide of iron. So the 8.4 grams is the mass of iron. Now let us calculate the simplest formula using the method that we have seen earlier on. So we shall start with the elements found in this compound. And the elements are iron and we have oxygen. Then we go to, instead of percentage composition now, we are going to deal with the mass of each element directly. So we go to mass, that's the mass composition of iron is 8.4, that one of oxygen is 3.6. Then we have to know or remind ourselves about the relative atomic mass of each element. So for iron is 56, oxygen is 16. So we go now to the moles of each element. So in getting the mole, we know that it is going to be the mass also. We divide by the relative atomic mass. That is for each element. 3.6 over 16. So what we get from the calculator is equal to, let us get it very fast, 8.4, we divide by 56. So this one has given me 0.15. Then 3.6 divided by 16. This one has given me 0.225. So this is our mole ratio in this case. I mean the number of moles of each element that we have got. So for oxygen is 3.6 divided by 16 and it is 0.225, and for iron is 8.4 divided by 56 and is 0.15. So these are the number of moles. Don't round off. Let's come to the mole ratio. So the mole ratio, we are going to divide by the smaller number of moles. Mark Q. This one looks to be longer, but we need to mind about the place values. This is ones, then we have tenth. In tenth, this one is 1 and this one is 2. So this one is bigger than this. And for that reason, we shall divide by the smaller number of moles. In this case, the mole ratio is 0.15. We divide this one by 0.15. This one also, it is 0.225. We divide by, these are yet the number of moles. Let's go to the mole ratio. So it is 0.15. We divide by itself, and then 0.225. We also divide by 0.15. Let us try to see what we get. In this case, what we get from here will be 1, a ratio of 1 to, so 0.225, we divide by this, and here we have exactly 1.5. Now try to see, we have a ratio of 1 to 1.5. So what do? We make sure that it is to 1 decimal place, if it is not to 1 decimal place. So in this case, 1.5 is to 1 decimal place. We are only going to convert it now to a fraction. Using our method as we saw, we shall make this one here, we shall do it as a side work. So it is 1.5. Therefore, we start somewhere from 0.5, then we go to 1.5. What do? We get the fraction that corresponds to exactly 0.5, which is a half. The one that corresponds to 1.5 is got by adding the denominator to the numerator, which is 3/2. Then we bring the fraction which corresponds to our 1.5. It will be 1 to 3/2 and multiply both sides by the denominator. So our ratio is 2 to 3. And then it means that our empirical formula is easy, or our simplest formula is Fe2 or 3. So we have got the simplest formula in this case. Now let us go to the next part, which is saying we should write the equation for the reaction that took place. The equation for the reaction that took place, we need to analyze this reaction here very well. The equation for the reaction that took place. What is reacting with what? I can see that here we passed dry carbon monoxide over a heated oxide of iron. The formula of the oxide of the iron we have got it is here, Fe2O3. We are passing dry carbon monoxide over it. So this one is now B part 1. So we are having Fe2O3. This compound is what we call iron 3 oxide. We are reacting heated iron 3 oxide with dry carbon monoxide gas. So what do we get in this case? The carbon monoxide will remove the oxygen atoms as a reducing agent, and we get iron remaining. As well, the carbon monoxide will be oxidized to carbon dioxide gas. Now let us try to balance this equation here. We have 3 oxygen atoms and 1 here. This is 2. So let us try to make the number of oxygen atoms go to 6 by multiplying carbon monoxide by 3. So 6 oxygen atoms, meaning that we multiply carbon dioxide by 3. 3 carbon atoms on the product side, on the reactant side also the same. Then on the reactant side, we have 2 ion atoms, and here on the product side, we have 1 ion atom multiplied by 2. So we have already got the equation for the reaction between the heated oxide of iron and then carbon monoxide. And finally, we go to Roman 2. They are saying, what is the industrial application of this reaction here? So if you see this iron 3 oxide, it is one of the ores of iron, or one of the compounds from which iron can be extracted or obtained. And iron, being a metal which is moderately reactive, it forms a compound which is not so stable, which is not also so unstable. And in this case, we can extract iron from its ore by the method of reduction using carbon monoxide. And this one is an industrial process which takes place at a large scale in industries. So this process here is applied, or this reaction is applied in the extraction of iron. So this one here, we shall look at it later. The extraction of iron which takes place in the blast furnace by the reduction of the ore of iron, in this case using carbon monoxide. So that is our part of the continuation of the calculation of empirical and molecular formula. Next is we are going to deal with a hydrated compound. So thank you for watching. Welcome back again to TED Talks Education. In this session, we are going to look at Avogadro's principle and the molar gas volume. Avogadro's principle and the molar gas volume. So let us start with what we call Avogadro's principle. Can you remember Avogadro? I told you something earlier that Avogadro is the father of the mole. He is the one who came up with the number of particles in one mole being 6.02 times 10 raised power 23. That's the number of particles in one mole of a compound. So it is the same Avogadro that came up with the principle that we are going to see. And that principle was used for coming up with what we call the molar gas volume. So let us look at Avogadro's principle. A principle is almost like a law, only that a law is supposed to be quoted. So a principle is just a step away from a law. So it's almost like we are talking of Avogadro's law, almost. But it is at the level of a principle which is so close to a law. So we cannot quote it. Now let us try to see the work of Avogadro that made him to come up with a principle called Avogadro's principle. What Avogadro did was he collected samples of gases. He picked different gases. Let me assume that Avogadro used nitrogen gas. Let me use the name nitrogen gas. He picked oxygen gas. He picked, say, carbon dioxide gas. He picked, say, ammonia gas. So Avogadro collected different samples of gases, and then he made sure that he used the same volume of these gases. So assuming that Avogadro used 50 cubic centimeters of nitrogen, it means that he also used 50 cubic centimeters of oxygen. He also used the same volume of carbon dioxide and the same volume of ammonia. Let us say these are the four gases that Avogadro used. Then he subjected these gases to the same conditions of temperature and pressure. Equal temperature, equal pressure, the same temperature. He subjected these different gases to the same conditions of temperature and pressure. Then he started looking for the number of moles in them. So he found out that in this case, the number of moles of these different gases having the same volume and subjected to the same conditions of temperature and pressure, he found that if nitrogen gas in the 50 cubic centimeters, if there was 0.1 mole, then he found that even oxygen had the same number of mole, that is 0.1 mole. If carbon dioxide 50 cubic centimeter, he looked for the number of moles in it. He also found that they were the same, 0.1 mole. Even ammonia had also 0.1 mole. This was his finding. So from his finding, he therefore came up with a principle, which I said is almost a law, which governs different samples of different gases. Different samples of different gases. I say that he used equal volume of those gases, but he subjected them to the same conditions of temperature and pressure. Equal temperature, equal pressure. Then he looked for number of moles in them. He found that they were just the same. This is a wonderful work of Avogadro, which made him to come up with a principle. So let us look at Avogadro's principle, what it states. So from this work we can state Avogadro's principle. Avogadro stated that in his principle, he stated that equal volume equal volume of all gases under the same conditions of temperature and pressure have equal number of moles. So this is what we call a statement of Avogadro's principle. Equal volume of all gases, remember all gases, not just some gases but all gases, provided that they are under the same conditions of temperature and pressure, they have the same or equal number of moles. So Avogadro's principle was then used for developing what we call the molar gas volume. So let us also look at the molar gas volume. So this molar gas volume is a brainchild of the work of Avogadro. So this one here, the molar gas volume, was got from Avogadro's work, from Avogadro's principle. Equal volume of all gases under the same conditions of temperature and pressure have equal number of moles. Now let us look at the molar gas volume. Molar in this case refers to 1 mole. Molar refers to 1 mole. So when I talk of the molar gas volume, it is the volume of 1 mole of a gas under certain standard conditions of temperature and pressure. So the molar gas volume is the volume of 1 mole of a gas, the volume of 1 mole of a gas under certain standard conditions, of temperature and pressure. Now we need to see the conditions of temperature and pressure used in this case for getting the volume of 1 mole of a gas in this case. So you can see we are talking of 1 mole, equal number of moles. Here Avogadro's principle says that equal volume of all gases have got the same number of moles. It means that equal number of moles also of all gases, provided that the temperature and pressure are the same, they will also have equal what? Volume. So if I have 1 mole of a gas under certain conditions of temperature and pressure, I will find that it has got some number of moles, or in this case if I have 1 mole, it will have got some volume, which is true for all gases. So it makes us to look at the values of the molar gas volume at certain conditions of temperature and pressure. Now the conditions of temperature and pressure in this case are: 1, we have what we call room temperature, at room temperature, and then at what we call standard temperature and pressure. Standard temperature and pressure. So sometimes we can give it the acronym STP, which is always used so freely. So we have 2 different conditions here of room temperature and then the standard temperature and pressure. Now let us try to look at the molar gas volume at room temperature and then the molar gas volume at STP, which are just the same because these are different standard conditions, but they are applicable to all gases. In this case, not liquids, not solids, we are talking of gases only. So let us try to see in this case starting with the first one, that is at room temperature. So 1 mole molar gas volume, the volume of 1 mole of a gas at room temperature. 1 mole of a gas at room temperature, it has the volume, that means each space which it occupies is 24 liters, and the 24 liters is the same as 24 cubic decimeters. Now, in terms of cubic centimeters, this value here we can multiply by 1000 and it gives us 24,000 cubic centimeters. So this is the molar gas volume at room temperature. So 1 mole of a gas at room temperature, equal volume of all gases under the same conditions of temperature and pressure, has got the same volume in this case, or the same number of moles, same volume. That is with the molar gas volume at room temperature. Then 2, let us look also at STP. So 1 mole of a gas at standard temperature and pressure, which is STP, it occupies 22.4 liters, and 20 liters in this case the same as cubic decimeters. So it is also 22.4 cubic decimeters, and multiplying by 1000 to get cubic centimeters, it will be 22,400 cubic centimeters. So the values of the molar gas volume at room temperature and at standard temperature and pressure are always given for a candidate to use in the calculations that we are going to see but later. So it can be given either on the front page, that is the first page of your question paper, or against each question, or at the end of a question. If they know you are going to use it, then they will give you the molar gas volume at that very condition. So do not so much get disturbed, because this one we shall be given just free of charge, just like the relative atomic masses. But it is imperative for a learner to also be able to remember the molar gas volume at room temperature. These values here, remember all of them. And then even at STP, you should be able to remember. So that's what we call Avogadro's principle, and that's what we call the molar gas volume. So we are now going to look at next how to use these values of the molar gas volume at room temperature and at STP to carry out our calculations. So thank you so much for watching. This is Tech Talks Education. I'm Achille, I'm Daniel, still taking you in O-level chemistry for Tech Talks. We are going to look at calculations of relative formula mass. Calculation of relative formula, or what we call relative molecular mass. So last time we looked at what we call relative formula mass. We said that in the actual sense it is a ratio or a quotient relationship whereby we have relative formula mass, let me call it RFM, being equal to the ratio of the mass of 1 mole of atoms of an element to 1/12 of the mass of 1 mole of carbon 12 atoms. So this expression gives us what we call the relative formula mass or the relative molecular mass of a compound. In this case, we are dealing with compound, not an element, of a compound. So it is the ratio of the mass of 1 mole of atoms, let me call it particles, of a compound to 1/12 of the mass of 1 mole of carbon 12 atoms. So we say that if we are to substitute for this and work it out, we shall find that we get a value which has got no unit completely. It's not in grams. So relative in this case means that there is a relationship of between two similar items with the same unit, and in this case the units cancel and you remain with just the values. So that is it. Now in the calculation of relative formula mass, we shall not be using this expression. Instead, we shall be using the values of the relative atomic masses of the elements which are found in 1 mole of that compound. We shall be adding the relative atomic masses of those elements. So let us take, for example, carbon dioxide. If I take carbon dioxide, the first thing that you need to do is to work out the formula mass of the compound so that you see the number of atoms of each element in one particle of that compound. So in carbon dioxide, we have carbon and oxygen, which are the elements in it. Now, carbon, O-level chemistry for Tech Talks. We are going to look at calculations of relative formula mass. Calculation of relative. Let us finally, for now, look at still moles in solution, but we are going to go to how to finding